Differentiability. It is possible that the limit that defines the derivative of a function f may not exist at certain points in the domain of f. At such points, the derivative is undefined. To account for this possibility, we make the following definition. So our first definition would be a function f is said to be differentiable at x0 if the limit f prime x0 equals to the limit h approximating to 0 and f x 0 plus h minus f x 0 over h exists. A function f is said to be differentiable at x0 if the limit exists. If f is differentiable at each point of the open interval a and b, then we say that it is differentiable on a and b. And similarly, for open intervals of the form a and positive infinity, comma, negative infinity, and b, and negative infinity and positive infinity. In the last case, we say that f is differentiable everywhere. So how's gonna supposed to be? I don't know. Geometrically, a function f is differentiable at x0 if the graph of f has a tangent line at x. Thus, f is not differentiable at any point at 0 where the second lines from p at 0 and function of x0 to point qx and function x distinct from p do not approach a unit non-vertical limiting position as x approximates to x0. The figure illustrates the common ways in which a function that is continuous at x0 can fail to be differentiable at x0. This can be described informally as corner points or points of vertical tangency. Or at a corner point, the slope of second lines have different limits from the left and from the right, and hence the two-sided limit that defines the derivative does not exist. At a point of vertical tangency, the slopes of the second lines approach positive infinity or negative infinity from the left and from the right. So again, the limit that defines the derivative does not exist. How's that gonna supposed to be lah? Slope towards blah blah blah. Oh. Pokoknya cintaku sama si Akli ibaratkan hidup mati. An illustrated figure. Differentially at x0 can also be described informally in terms of the behavior of the graph of f under increasingly stronger magnification of the point, blah blah blah. It is if f is differentiable at 0, then under sufficiently strong magnification of the point looks like a non-vertical line, a tangent line. If a corner point occurs at 0, then no matter how great the variation of it, the corner persists and the graph never looks like a non-vertical line. And if vertical tangency occurs at 0, then the graph of that looks like a vertical line under sufficiently strong magnification at p. Differentiable, not differentiable, not differentiable. The relationship between differentiability and continuity. We already know that the functions are not differentiable at corner points and points of vertical tangency. The next theorem shows that the functions are not differentiable at a point of discontinuity. We will do this by proving that if f is differentiable at a point, and it must be continuous at that point. So our second theorem is that if a function f is differentiable at x0, then f is continuous at x0. So continuity means differentiability, or differentiability means continuity. Yeah, whatever lah. Given that f is differentiable, blah 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 blah. Oh. The relationship between continuity and differentiability was of great historical significance in the development of calculus. The early 19th centuries, blah 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 blah. So what? Such functions have started to play a fundamental role in the study of geometric objects called fractals. Fractals are very unordered to natural phenomena that were previously dismissed as random and chaotic. I see. Okay.